If you've got a dark mode IDE glowing on your second monitor right now, or maybe you're tracking down a memory leak that just won't replicate, welcome.
Yeah, you were definitely in the right place.
This deep dive is custom built for you. Tonight we are tackling one of the most pressing, mind-bending systems engineering puzzles in machine learning today.
It really is a fascinating puzzle.
We've got a stack of fresh source material here, research papers from top AI labs, preprint studies on scaling laws, and engineering blogs from infrastructure teams.
All trying to answer the same big question.
Exactly. Our mission is to figure out what exactly happens when AI trains on AI. We're unpacking the architecture, the math, and really just the sheer computational chaos of synthetic data.
And it is a critical topic, largely because the industry has hit a massive bottleneck. I mean, for years, the brute force playbook for training large language models is simple, right?
Yeah, just scrape the internet.
Right. Scrape the entire public internet, every open source repository, every forum thread, every piece of documentation out there. But we are quite literally running out of internet.
Yeah, the sources refer to this as hitting the data wall. And I kind of want to frame this for the systems engineers listening. It's like, we spent the last decade building this revolutionary data guzzling engine.
A massive engine.
Yeah, and we know the physics of the engine work, the architecture scales beautifully, but right as we want to build a version 10 times larger, we realize we've pumped the last barrel of fuel on Earth.
We've tapped it all.
We've tapped GitHub, we've tapped Stack Overflow, we've scraped every wiki. The demand for tokens to satisfy current scaling laws is just vastly outpacing the supply of high-quality human-generated text.
It is.
So, I mean, the logical engineer's solution, like a perpetual motion machine, is to just have the machine print its own fuel, right?
It's an incredibly seductive idea. If you have a system that outputs highly coherent text and code, and a system that requires text and code to train, well, connecting the exhaust pipe directly back to the intake valve seems like the ultimate closed loop.
Right. You'd never have to worry about data scarcity again.
Exactly. You never have to worry about it. But the reality of running that loop is a structural nightmare. The urgency to use synthetic data is intense because, like you said, if we hit that data wall, progress fundamentally stalls.
The whole industry just grinds to a halt.
Right. But treating synthetic data as an infinite unmanaged fuel source leads directly into an architectural trap.
Which brings us to model collapse. And I want to be clear based on the research we're looking at here. Model collapse is not a theoretical white paper concern.
No, it is a mathematically demonstrated phenomenon.
It happens when models are iteratively trained on synthetic data from previous model generations. The result is an irreversible degradation in quality and just a massive loss of variance.
It's a very real compounding issue.
Let's try to map this to something we deal with all the time. Think about lossy compression algorithms, like saving a JPEG. If you compress an image, the algorithm throws out the data it calculates, your eye won't notice.
Right, it looks fine at first.
It looks totally fine, but if you open that JPEG and save it again with the same compression and repeat that process 50 times, the artifacts compound. You get macro blocking.
The image just degrades into a jagged, pixelated mess.
Exactly. It's a recursive loop of rounding errors.
That's a really solid parallel. In machine learning, it's a recursive loop of probability errors. To understand why it happens, we have to look at the statistical mechanics of these models.
The math behind the curtain.
Right. They are, at their core, probability distributions. When a model generates a sequence, it favors the center of the bell curve. It outputs the most likely, the most common, the safest tokens.
But in doing so, it actively undersamples the tails of the distribution.
Exactly. It ignores the outliers.
Let me jump in here because this is where the mechanics get tricky for me. If a model is already generating output at, say, a 90% quality threshold, why doesn't an echo chamber of its own outputs just maintain that 90%?
That's the intuitive thought, yeah.
Like, why does the variance actively shrink? It seems like it should just plateau, not collapse completely.
Well, it's because of generation over generation error compounding. You have to remember that organic human data is incredibly noisy and highly varied.
Right. Human code is a mess sometimes.
Exactly.
Right.
It contains rare solutions, bizarre edge cases, and sometimes brilliant unconventional code structures. A model might learn a highly efficient but rare sorting algorithm from human data, but assign it a low probability.
So it knows it, but it's not likely to use it.
Right, say a 2% chance of generating it.
Okay, so when we ask the model to generate 1 million synthetic examples, it almost never chooses that 2% algorithm. It just outputs the standard high probability boilerplate.
Exactly.
Right.
So the resulting synthetic data set has virtually zero instances of that rare algorithm. The tails of the distribution are just cut off entirely.
Wow. Okay, I see where this is going.
Now, you train the next generation model on that synthetic data set. This new model learns that the rare algorithm doesn't just have a low probability. It learns that it simply doesn't exist.
Because it wasn't in the training data at all.
Right. It's structural amnesia. Over successive generations, the model forgets the rare information and over-indexes on the most common patterns until the output becomes a repetitive, collapsed sludge.
The latent space literally shrinks.
Yes, it collapses inward.
Structural amnesia, that's a great way to put it. And the papers use the word irreversible. Once you bake that smoothed out, low-variant synthetic data into the foundation of a model, you can't just run a patch to fix it.
No, you really can't.
The weights have adjusted to a flattened reality. You've poisoned the well.
You have. And reversing it would require retraining from scratch with a pristine, high-variance data set.
Which, as we've established with the data wall, we are rapidly running out of.
Precisely. We don't have the fresh human data to hit reset.
So, if unmanaged synthetic loops cause irreversible model collapse, why are the major AI labs pouring billions of dollars into synthetic data pipelines right now? I mean, it can't just be desperation, right?
Yeah, there's a very deliberate engineering strategy there.
Looking at the architecture specs in these sources, there are distinct exceptions to the collapse rule. Synthetic data actually works brilliantly, provided it is generated under incredibly strict constraints.
Yes, very strict guardrails.
And the biggest constraint, like the escape hatch out of the JPEG compression loop, is verifiability.
Verifiability completely changes the math. Model collapse happens because you are relying on the model's own probabilistic vibe to determine what goes into the next training run.
It's grading its own homework.
Exactly. But if you have an external deterministic system to evaluate the output, you break that recursive loop.
And for software engineers listening, the ultimate external deterministic system is a compiler. We don't need a language model to guess if a Python script works.
No guessing required.
We can just spin up a sandboxed execution environment and run the tests.
That is precisely the mechanism.
Yeah.
The research shows that code generation is currently the most successful domain for synthetic data for this exact reason.
Because it's binary. It works or it doesn't.
Right. You instruct a model to write a complex function, generate unit tests for it, and then you execute the code against those tests. If it fails, the data is discarded or sent back for a fix.
Then if it passes?
If it passes, you now have an objectively verified high-quality data point. The compiler acts as an absolute ground truth anchor. It filters out the probabilistic noise before it can compound.
I want to push back on the scalability of that, though. Sure, spinning up a sandbox for a few thousand Python scripts is easy, but these models need trillions of tokens.
They do.
Integrating a headless compiler into a massive distributed training loop to verify billions of generated code snippets sounds like an infrastructure nightmare. I mean, the compute overhead just to verify the synthetic data must be astronomical.
Oh, the compute overhead is massive, and you're hitting on the core infrastructure challenge labs are facing right now. We aren't just talking about generating data.
Right.
We're talking about running parallel verification environments at an unprecedented scale. But the alternative is hitting the data wall and halting all scaling progress.
So it's just a cost of doing business now.
Exactly. The compute cost of verification is deemed entirely necessary.
Okay, so we have verifiability for domains like code or math, where there is an objective right answer. But the sources also highlight a second major exception to model collapse, which is distillation.
Yes, distillation is fascinating.
How does distillation work mechanically without causing that same structural amnesia?
Distillation works because the flow of information is strictly asymmetrical. It's a top-down architecture. You have a massive frontier-level AI model, the teacher.
Like the biggest models available.
Right. It have hundreds of billions of parameters. It costs a fortune to train on pure human data, and it is highly capable, but very slow and expensive to run. Then you have a much smaller, faster student model.
So instead of the student model trying to learn from the raw internet, we use the massive teacher model to generate highly structured, complex synthetic data to train the student.
Yes, but it's deeper than just generating data. In a true distillation setup, you aren't just giving the student the final answer. You are minimizing the difference between the teacher's probability distribution and the student's.
Wait, how do you do that?
The teacher model provides its chain of thought, its reasoning steps, and even its logits.
The raw probability scores.
Exactly. The scores it assigns to different words. The student model learns to mimic the internal logic of the superior model.
But wait, if the teacher model is generating the data, isn't that still synthetic? Why doesn't the student model suffer from model collapse?
Because you aren't recycling a model's own outputs back into itself. The student isn't learning from its own smoothed-over approximations. It's being pulled upward by a superior oracle.
Okay, so the teacher model acts as the quality filter.
Right. Now, to be fair, if you try to use that student model to train a third model and a fourth, you will eventually hit collapse.
You eventually degrade the signal.
Yeah. But for a single generation transfer, say, from a massive server farm model down to a model small enough to run on your laptop, distillation is incredibly effective.
This completely reframes how I was looking at this. It takes the idea of synthetic data away from being this magical, infinite text generator and turns it into a grueling systems engineering problem.
It's all systems engineering at this point.
Knowing that verifiability and distillation are the keys, how do infrastructure teams actually build this? The engineering blogs we pulled outline a very strict 4-stage pipeline required to make this work. Generate, filter, validate, and mix.
And if a team fails at any single one of those 4 stages, the entire dataset is compromised.
Let's break that down because there's a lingering perception out there, especially outside of ML engineering, that synthetic data is just a cheap shortcut.
Like they're just taking the easy way out.
Right, like a company doesn't want to pay human domain experts, so they just write a script that says, while true, generate data. But looking at this pipeline, setting up this infrastructure seems vastly harder than just scraping Wikipedia.
Oh, it's exponentially harder.
What actually happens mathematically if a dev team gets lazy and skips the filtering stage? The sources refer to this as naive generation.
Naive generation is the fastest route to ruining a model. And mathematically, it results in severe statistical bias amplification.
To clarify for everyone listening, when we say bias here, we're not necessarily talking about sociological or ethical bias, although that can happen.
Right, that's a separate, very real issue.
But here we are talking about statistical bias, data skew, overrepresenting certain vectors in the latent space.
Precisely. Let's say your original human training data has a slight statistical preference for a specific coding idiom or a particular syntactic structure in SQL queries.
Okay.
Maybe it appears 55% of the time when there are other equally valid approaches. If you run naive generation, just asking the model to output data without a secondary filtering mechanism, the model will latch on to that 55% preference.
Because it's the safest bet.
Right. So in the synthetic data set, that idiom might now appear 85% of the time.
Because it's over-indexing on the highest probability tokens.
Exactly. Then you train the next model on that synthetic data. The 85% presence becomes overwhelming. The new model will essentially hard-code that idiom as the only valid way to write a SQL query.
Wow. It amplifies a slight statistical skew into an absolute structural rule.
It forces a monoculture.
So how do you engineer a filter to catch probabilistic drift? You can't just use rejects for that.
No, absolutely not. You have to build and run massive secondary reward models. These are entirely separate ML systems whose entire job is to score the variance and quality of the generated data.
So AI checking AI.
Yes. They look at the distribution of the synthetic batch and compare it to the original human distribution. If the synthetic batch is missing those rare edge cases we talked about earlier, the reward model slides it, and the generation parameters have to be adjusted.
It's like trying to build a highly complex water purification plant, but the water is rushing through the pipes at terabytes per second. You have to catch the statistical toxins before they hit the reservoir.
That is a very accurate analogy.
Okay, so we run these heavy reward models to filter. We use compilers to validate. What about the final stage mix? The sources emphasize that you can't just train on 100% synthetic data, even if it's verified.
Data blending is arguably the most difficult art in this entire pipeline. You have to mix the synthetic data with pristine human data. Usually it involves curriculum learning or annealing phases.
Annealing. I know annealing in metallurgy is heating metal to change its properties and then cooling it slowly. How does that apply to a data pipeline?
Well, in training, you might use the vast ocean of verified synthetic data for the bulk pre-training phase. It helps the model learn the fundamental logic, the basic structures, the syntax.
It builds the foundation.
Right, the heavy lifting. But you save your highest quality, most diverse, perfectly curated human data for the final phase of training, the annealing phase.
Okay, so you expose the model to the messy, high-variance human data at the very end.
Yes, to sharpen its edges, to teach it the rare algorithms and the nuanced edge cases that the synthetic data moved over.
So even with the most rigorously engineered, multi-million-dollar synthetic pipeline, human data is still the ultimate premium asset. We never actually escape the need for human variance.
We don't. And that leads directly to where the industry is heading. The sources universally point out that the most promising architecture for the future isn't AI working autonomously in a dark server rack.
Right.
It's human-AI collaborative curation.
Like scaling up RLHF reinforcement, learning from human feedback, but treating humans as the ultimate integration test. In this collaborative cycle, the AI generates data at a massive scale, and humans curate, correct, and inject variants. Then the cycle repeats.
Yes, but it's important to clarify the type of human intervention required here. We aren't talking about crowdsourced workers clicking on images of crosswalks and traffic lights.
Right, the tasks are way too complex now.
Exactly. As models get more advanced, the synthetic data they generate gets highly complex. If a model generates a synthetic dataset of advanced cryptographic algorithms, you need postdoctoral mathematicians and senior systems architects to review it.
So to use a software engineering parallel, it's like the LLM is the ultimate junior developer.
I like that.
This system can act as a massive concurrent thread generator, writing tens of thousands of lines of boilerplate and basic functional logic overnight. Unbelievable volume. But the human is the senior architect who has to come in, look at the pull requests, and do the brutal code review.
That's exactly how it works.
The junior dev AI solves the volume problem, the data wall. But the senior architect, human, ensures the architecture doesn't collapse under the weight of its own rounding errors.
That is a great framing. The human injects the required variance back into the system. The model simply cannot generate the true ground truth novelty on its own without eventually circling the drain of its own probability distribution.
It needs us to break the loop.
Yes, this collaborative loop is the only sustainable answer to the scaling laws. Volume through hardware, variance through human intellect.
It is wild that we started this deep dive talking about the sheer panic of running out of human data on the internet, and the ultimate engineering solution isn't to replace the human, but to elevate the human to the role of the final, irreplaceable filter.
It's a very elegant shift in perspective.
Let's recap the architecture we've mapped out tonight. We started with the hard physics of the data wall, the realization that scaling laws are starving for tokens. We looked at the recursive trap of model collapse, where generation over generation probability errors lead to structural amnesia and a flattened latent space.
The dreaded pixelated JPEG.
Yes, exactly. We found the engineering escape hatches, strictly verifiable execution environments, like compilers in the training loop and asymmetrical distillation from massive teacher models. We broke down the heavy compute required for the generate, filter, validate, and mix pipeline to avoid statistical bias amplification.
Right.
And finally, we arrived at the human-in-the-loop annealing phase, where domain experts provide the necessary variance to keep the models sharp.
It is a staggeringly complex distributed ecosystem.
It really is. But before we sign off and let you get back to your own debugging, there's one more piece of the infrastructure puzzle from the sources that we need to throw into the mix. A provocative thought to mull over while your tests are compiling.
Let's hear it.
We spent this entire time talking about synthetic data pipelines as massive centralized infrastructure, giant server farms running reward models and compilers.
Yeah, massive data setters.
But as distillation gets better, these highly capable models are shrinking. What happens when these models don't live in a data center? What happens when a highly capable model needs to run locally on an edge device, on your phone, your watch, or an offline environmental sensor?
That completely changes the topology.
Exactly. How does the synthetic data loop change when the AI is in your pocket, generating and training on synthetic data locally, isolated from the global distribution? If millions of edge devices are running their own tiny recursive loops, what does that do to the network?
That introduces localized model collapse and federated learning drift. The mathematical complexity of syncing those distributions back up is a completely different order of magnitude.
It really is something to think about the next time your phone auto-completes your code or your text. Thanks for joining us on tonight's deep dive. Keep building, keep verifying, and we'll catch you on the next one. Have a good night.